In this lecture, we're going to talk about autonomous systems of two first-order differential equations, and we're going to use the technique known as linearization, which we've seen before in this course, near constant solutions to understand what the nonlinear, what the solutions to the nonlinear system look like. So linearization is a recurring theme in differential equations. We started seeing it in chapter 2 when we did the linear drag model. Actually, in chapter 1, Newton's law of cooling was a linearization. We saw it in chapter 3 when we modeled spring forces as just being proportional to the displacement, and when we derived the pendulum linear differential equation from the nonlinear differential equation. So it's a very important technique. And you can linearize higher order differential equations as well as systems of nonlinear differential equations. And we'll use that to understand stability questions and the solution behavior for the original nonlinear systems, autonomous systems of differential equations. Okay, so in order to do linearization for a system of first-order differential equations, we're going to end up having to use multivariable calculus. This shouldn't surprise you. And we're going to, in particular, use the tangent approximation formula. Sometimes this is called the affine approximation formula for differentiable functions of two variables. And if you've forgotten that formula from multivariable calculus, I can remind you of it with a concrete example. And here's the setup. So suppose it's currently 45 degrees downtown. If you live in Salt Lake City, our coordinate grid is set up with an origin at Temple Square. So that will be what we call downtown. And that'll be the origin of our coordinate grid. Okay, and suppose that within several miles of downtown, if you go north, which we'll call the we'll call it the north direction, the temperature decreases by about 0.2 degrees per mile. And we'll assume that as you go east, it decreases by about 0.5 degrees per mile, maybe because you start running into mountains. Okay, and we'll assume that the rate of change of temperature is, actually it follows, is the opposite if you're going south and west, respectively. Okay, so here, given that information, let's try to estimate the temperature at the airport, which is about 8 miles west and 2 miles north. So on our coordinate grid, marked off in miles, it's located at about 8 minus 8, 2. Okay, so what is the temperature at the airport? Well, a good zeroth order approximation would be just the temperature at downtown. So T at minus 8, 2 is about T downtown plus. Well, we are told that as we go east, the temperature decreases at a rate of about 0.5 degrees per mile. Okay, so that's actually, let me write that as how fast the temperature is changing in the east direction. And we're assuming that rate of change of temperature is pretty much constant within 10 miles. So I'll just put in, so that's the value at the origin. Okay, and let me fill in numbers at the same time. So T of 0, 0, that's the temperature downtown, that's 45 degrees. Okay, now how fast, so to get how much it's changed between downtown and the airport, I have to take it, as I move in the east direction, I have to put in how fast it's changing in the east direction, which is degrees per mile. And then I have to multiply by the change in the east direction, which has units miles. So I get degrees. Okay, so the rate of change in the east direction is negative 0.5 degrees per mile because the temperature was decreasing in that direction, and the change in the east direction was negative 8 miles. And that's accounted for the temperature change as I'm moving east, but then I still have to move north. And so I'll use how fast it's changing in the north direction, and so that's in degrees per mile, times how far north I went. And it is changing, it is decreasing by 0.2 degrees in the north direction, and I went 2 miles north. Okay, so to summarize, I went 8 miles west. That decreased my temperature. Now that increased my temperature by 4 degrees. So I started at 45 degrees. So after going 8 miles west, it was 4 degrees warmer. And then I still had to go 2 miles north, which decreased the temperature by 0.4 degrees. So in net, my temperature changed by 3.6 degrees as I went from downtown to the airport. Okay, and so that gives me an answer of 48.6 degrees for the temperature at the airport. Okay, so the strict definition of a function of two variables being differentiable at a point x naught, y naught, and this is from multivariable calculus, is that we can estimate f at x naught plus delta x, y naught plus delta y, by f at x naught, y naught, plus the rate of change in the x direction at x naught, y naught, times how far we went in the x direction, plus the rate of change in the y direction at x naught, y naught, times how far we went in the y direction, and then plus an error term, which I'll write as, say, epsilon of delta x, delta y. And then f is differentiable in the multivariable sense if and only if the limit as delta x, delta y goes to 0, 0 of the error term divided by the magnitude of the vector delta x, delta y is 0. So that's saying that the error is shrinking faster than the approximation terms that we get from the partial derivatives. Okay, and so hopefully that's a good review. Now let's talk about linearization using our rabbit squirrel competition model from the previous lecture. So if I remember correctly, which I don't guarantee, x of t is the rabbit population and y of t is the squirrel population. All right, so let's look at the origin, which was one of our 4 equilibrium points. So recall, and we can see from the p-plane picture that the equilibrium points were 0, 0. That was kind of boring. No rabbits at 7, 0. Sorry, all rabbits at 7, 0. All squirrels at 0, 8. And then the super interesting one was when there were both rabbits and squirrels, and that was 4, 6. And remember, our units could be like thousands of rabbits and thousands of squirrels. So the number 4, 6 is sensible. Okay, so let's look at the origin. Well, we've got our tangent approximation from the previous page set up for us because the f of xy, which was the rabbits, and the g of xy, which was the squirrels, are already set up so that we can see the linear terms and the quadratic terms, which we throw away. Because as xy goes to the origin, the quadratic terms shrink much faster than the linear terms. So that's an easy linearization. Okay, well, you can see that the solutions for x of t, this is just an exponential growth problem, are just c e to the 14t, because x prime is 14x, and y of t, let's say x of t is c1 times e to the 14t, and y of t is c2 e to the 16t, where the c1 and c2 are like the x naught and the y naught. And in terms of our eigenvalue, eigenvector analysis, the eigenvalues of this diagonal matrix are 14 and 16. And so, and the eigenvectors are 1, 0, and 0, 1. So we could have also written the solution in the second form, which you'll see is the same as I wrote it there. All right, so we know we have 2 positive eigenvalues, that the origin is a nodal source for the linearized problem. for the linearized. dE. And in this picture here, the bottom picture is the phase plane for the linearized dE. And then for the actual dE, when x and y are small enough, that system, x prime equals 14x minus 2x squared minus xy, and y prime equals 16y minus 2y squared minus xy, it makes sense that the solutions for that nonlinear system will look close to the solutions for the linearized system, and sure enough, that's right. So you'll notice on this graph of the linearized system near the origin, it's only going from minus 0.2 to 0.2 in both directions. It looks very much like what would happen if you magnified the nonlinear solutions near the origin. And actually, it looks like the linearization is effective way out to like plus or minus 2 in terms of describing what the nonlinear solutions look like. Okay, so that's linearization illustrated in a case where it was easy to linearize. Now, let's use the multivariable calculus approximation formula to do this process at points which are not the origin. Okay, so we start at an equilibrium point, x star, y star, which is the value of a constant equilibrium solution. And since it's a constant solution to the nonlinear system, x of t and y of t are constants, so x prime and y prime are 0. So f of x star y star is 0 and g of x star y star is 0. Yeah, we've talked about this before, but it's going to be useful when we do the approximation. Okay, so now what we're going to do is we're going to change functions. We're going to add constants, or actually subtract constants, which is the same thing from the functions x of t, y of t. And we're going to do this in a way, and then the new functions are going to be what we call u of t and v of t. So we had the original xy grid where the parametric curve, solution curve x of t, y of t was going. And u of t is going to be, okay, and we've got the point x star, y star, which is the constant solution. U of t is going to be the deviation from x of t to x star, which is just x minus x star. So here is x star. Here is x of t. And u of t is x minus x star. And here is y star. And maybe here is y of t at some instant. And v of t is just going to be y minus y star, which would be negative in this picture. So what this means geometrically, so for example, if x equaled x star and y equaled y star, u and v would be 0. What this means geometrically is that it's as if we're making a new coordinate system, a uv coordinate system, based at the point x star, y star. So in this picture, I drew the values of x of t and y of t, so the point x of t, y of t would be here. And in the UV coordinate system, it would be u of t, v of t. So this would be u of t, and this would be v of t in the UV coordinate system. All right, and we can write how these pairs of functions are related either by writing u and v in terms of x and y, or the other way. Now, u of t and v of t differ from x of t and y of t by constants, so that's why u prime of t is the same as x prime of t, and v prime of t is the same as y prime of t. But x prime is f of xy, and y prime is g of xy, because we are starting with a solution to the original nonlinear system. And now we'll use the tangent approximation. So x is x star plus u of t, and y is y star of v of t. So we'll rewrite f of xy as f of x star plus u, y star plus v, and the same for g. Okay, so now looking at this identity and looking at the left side and the right side, we have u prime at t is f at x star plus u of t, y star plus v of t. And now we use the tangent approximation from the warm-up exercise to write that as f at the base point, x star, y star, plus how fast f is changing in the x direction times the change in the x direction, which is u, plus how fast f is changing in the y direction times the change in the y direction, which is v, plus the error term. And we do the same thing for v prime. Okay, we're at an equilibrium point though, so f of x star, y star is 0, and g of x star, y star is 0. And now what we do for the linearization is we figure that when u and v are small, the epsilon 1 and the epsilon 2 are negligible compared to the linear terms, and so we just throw them away. So in fact, if I was looking at exact solutions, u prime, v prime would be the contributions from the linear terms, which I wrote in matrix form, plus the epsilon 1 of u and v and the epsilon 2 of u and v. But because I don't know how to deal with those nonlinear terms, I just assume that I've started close enough to x star, y star, so that u and v are small enough so that I can throw these away. And that's the process of linearization. And I'll look at the solutions to the linear system of DEs and use that to approximate the solution to the nonlinear ones. All right, so remember from multivariable calculus that 2x2 matrix is the Jacobian matrix for the vector function f of xy, g of xy. And it's been evaluated at the base point, at the equilibrium point. Now, we'll be computing a lot of Jacobian matrices, so in case you haven't seen it before, you can do a lot less writing if you just write f sub x for the partial of f with respect to x and f sub y for the partial of f with respect to y. And as long as you know what point you're evaluating it at, you don't have to put that in. And so by writing the Jacobian matrix this way, I save a lot of writing. Okay, so now let's do the linearization for that rabbit-squirrel competition model. And remember, in the linearization, we're getting solutions u of t, v of t, which are telling us how much xy varies from the point 4, 6. Here we go. So let's compute the Jacobian matrix for fg. And I might say at the point xy first. So that'll be f sub x, f sub y, g sub x, g sub y. Okay, f sub x, looking up at f of xy, partial f with respect to x is going to be 14 minus 4x minus y. F sub y, I only get the third term, and I get the minus x. When I compute the partial derivative of g with respect to x, I just get minus y. And when I compute the partial of g with respect to y, I get 16 minus 4y minus x. So that's the Jacobian matrix of fg. At any point xy, I need to evaluate it at the equilibrium point, 4, 6. Okay, so at 4, 6, I get 14 minus 16 is negative 2 minus 6 is negative 8. And I was just checking my work. And the f sub y is just negative 4. And the g sub x is negative 6. And the g sub y is 16 minus 24 minus 4. That's 16 minus 28 is negative 12. Oh, and that's right. That's what I was supposed to get. And then the solutions to that linear system will give us approximations for the deviations from x star and y star in the original nonlinear system. All right, so we could find the eigenvalues and eigenvectors. It's easy to use technology, and it turns out that p-plane will just do this for you if you click on an equilibrium point. I'll show you in a second. So we have two negative eigenvalues. Those are the eigenvectors. So we know that for the linearized system, we have what? We have a nodal sink at the origin, which is the equilibrium point for the linear system for UV. All right, and remember how we drew these. If you want to practice, you could try drawing it first. But I'll just go ahead and do it here. So V1 is about 0.79 minus 0.64. And so the lambda 1 eigenspace is all multiples of that, of the position vector. So this is the eigenspace for lambda equals lambda 1, let's say, which is negative 4.7. And for lambda 2, the eigenvector is about 0.49, 0.89. And the eigenspace of position vectors is all multiples of that. Our general solution, U of t, V of t, is all linear combinations of e to the lambda 1, which is minus 4.7 t, v1, which is 0.79 minus 0.64, plus c2 e to the minus 15.3 t times 0.49.89. Okay, so if we start out on the lambda 1 eigenspace, c2 is 0, and I just, u of t, v of t decays exponentially to the origin. If c1 is 0, then I'm starting out on the lambda 2 eigenspace, and I decay to the origin even more quickly as t goes to infinity. If c1 and c2 are both non-zero, then the e to the minus 15.3 t decay term decays much faster than the e to the minus 4.7 t term. So I will come in tangent as t goes to infinity. I'll converge to the origin tangent to the lambda 1 eigenspace. And if I let t go to minus infinity, it's the e to the minus 15.3 t term that dominates, even though both terms are going to infinity. But so I'll end up becoming tangent to the lambda 2 eigenspace. Okay, so that's what the solution to the linearized system looks like at the UV origin. How did we do? Okay, so here was the nonlinear system and the equilibrium point 4,6 and the nonlinear system solutions. If you want p-plane to do the linearization for you, all you have to do on p-plane is use the find an well, so first you go to the solution menu item, and in that menu item there is find an equilibrium point. It will ask you to click near the equilibrium point. It will try to find it for you, and then it will compute the Jacobian matrix and the eigendata right here. And that's what we were using in the last problem. Okay, and here is the solution of the linearized system, which was u prime v prime is minus 8, minus 4, minus 6, minus 12 times uv. That was giving us that the origin in the UV system corresponded to the equilibrium point in the XY system. So this picture here, in this picture the U and V's are going between plus or minus 0.5. this picture is supposed to tell us what the nonlinear solutions look like near the equilibrium point. And you can see it does. All right, and to emphasize the connection between the x of t and y of t and the u of t, v of t again, the u of t, v of t are measuring the deviations of x of t, y of t from x star, y star. Okay, so that's how you do linearization. Now there's a theorem that we can't prove in this course because it takes some heavy-duty analysis that says in 5 of the 6 cases we've considered that if the linearized solutions look like they did in the previous section, in other words, they're a nodal sink, a nodal source, a saddle point, a spiral source, or a spiral sink, then the nonlinear solutions look just like, how's that for mathematical rigor? Look just like the linear solutions at the corresponding equilibrium points. And so you can deduce stability questions for the nonlinear system, for example, just by knowing the stability answers for the linearized systems. So if the linearized system looks like a nodal sink, then the nonlinear equilibrium point is asymptotically stable, and the solution trajectories near that equilibrium point look just like the ones for the linearized problem. If the linearization is a nodal source, then for the nonlinear problem, it also looks like a nodal source near the equilibrium point, and that equilibrium point is unstable. Similarly for saddle points. Similarly for spiral sources. Similarly for spiral sinks. Asymptotically stable. The one case that you can't figure out from the linearization is the case where the linearization is a stable center. And that happens when the real part of the eigendata for the Jacobian matrix is 0. Okay, so that's a fun theorem that I think gets proven in the advanced undergraduate course in differential equations, when we're going to use it. Okay, so to end this lecture, let me talk a little bit about more about the borderline case. And you'll see in this week's homework that borderline cases show up several times, and there will be a way to figure out in some borderline cases whether you really do have a stable center for the nonlinear system or not. Okay, so here is 3 examples. So the system x prime equals minus y, y prime equals minus x has solutions which are circles, and it's a borderline, so it's a stable center, and it's borderline because the matrix for this linear system is 0, -1, 1, 0. This system, we've seen it before, arose by converting the unforced, undamped oscillator equation x double prime plus x equals 0 to a first order system. And you've drawn pictures for things like that, and you know that you get elliptical solutions. In any case, the determinant of this matrix, you can see just by putting minus lambdas on the diagonal, is lambda squared plus 1, which has roots lambda equals plus or minus I. And we knew it was a stable center from the pictures. And in fact, without even knowing the solutions, we could just take d by dt of x squared plus y squared and show its constant using the differential equation system. And that will show that x squared plus y squared is constant, so the solution trajectories are circles. Okay, so by the chain rule, this is 2x x prime plus 2y y prime, which from the differential equation is 2x times minus y plus 2y times x. Those terms cancel, and I get 0 for all time. So x squared plus y squared is indeed a constant for any solution trajectory. Okay, now let's add some terms and make a nonlinear system. So what I'm going to add is, so this is from the previous one, I'm going to add a negative multiple, well, a multiple of the position vector minus x minus y. And if you think about this, if you're at a, so first of all, 0, 0 is still an equilibrium point. Because it's 0, 0, the right-hand side is 0. Furthermore, if you think geometrically about what's going on, if you were to point x, y, then the vector minus y, x is perpendicular to the position vector x, y. It will actually be the tangent vector to the circles in the previous case. And then you're adding a multiple of the position vector xy. And if sine of r was positive, which it is for 0 less than r less than pi, you in this example, would be adding a vector which was pointing back towards the origin. And so the sum of those two vectors, instead of being tangent to a circle, would be the tangent vector for something which is pointing towards the origin. And as you can see from the picture, for the nonlinear system, you get a spiral sink. So in the first example, 0, 0, was a stable center. In the second example, 0, 0 is a spiral sink, even though the linearization at the origin, where we throw away all the higher order terms, is the same. And we can actually prove that the x of t, y of t are converging to the origin, or at least their magnitude is shrinking, by doing the same thing we did in the first case. We can take d by dt of r squared, which is x squared plus y squared. It'll still be 2x x prime plus 2y y prime, and that's 2x times, I'm just looking at the system, minus y from the linear part, but then I get plus sine of r times minus x, and then the 2y is 2 y prime is 2y times y prime is x minus sine of r times y. Okay, now let's look at what happens. The minus 2xy and plus 2xy cancel, and everything that's left has a sine of r in it, and what's left is minus 2x squared minus 2y squared. So I get sine of r times minus 2r squared. So if r is between 0 and pi, sine of r is positive, and this is strictly negative. So that says r squared is decreasing on the solution trajectories, and with more work, you could actually prove that r squared is going to 0. And so that's why you get the spiral sink there. And if you just change the sign of the correction term in example 3, you could do the same analysis as we did in example 2, and that's why we would get a spiral source at the origin. Even though the linearization in all three cases is what you started with in the first example. So this really illustrates how borderline the stable center case linearization really is. And it's an illustration of something cool that we haven't seen before. So in the n equals 1 case, back in chapter 2, we got equilibrium points and arrows. That was easy. In this chapter so far, we've seen equilibrium points and we've analyzed their stability. But in this example and this example, we get what are called stable orbits. Stable and unstable orbits. Orbits are periodic, well, in this context, they're periodic solutions, like orbits of planets. And you can see that if the sine of r was 0, in other words, at r equals pi, then the correction term is gone, and if you start out on that circle, you're just going to go around that circle. And in this middle picture, you can see, and it can be proven, that if you happen to start with an x naught whose distance to the origin was anything between 0 and pi, or anything between pi and 2 pi, then as t went to infinity, x of t would actually converge to this circle that's going radius pi. And so this is the state, so this is the circle of radius pi is a stable orbit. And if you happen to go out to 2 pi, you would get the opposite, which is called an unstable orbit. So here, this one is unstable. You can see that if I start with radius between 0 and pi, or between pi and 2 pi, I run away from that circle of radius pi. Okay, that's the end of